Well, thanks, Rich. Thanks, everyone, for being here for part two of the talk. Uh, Basically, what I'd like to do today is kind of continue on some of the threads we talked about on the previous tutorial. We talked about why traffic engineers should care about automated vehicles and specifically what the vehicles are doing on the traffic sensing side. What I'd like to do today is mostly focus on traffic control, but not losing sort of track of that big picture. What do these technologies solve and where do they leave? Where do they leave gaps? So before we dive into the control side, I just want to give kind of a reminder of, the critical issues that are basically outlined in a report by the U.S. National Academies. And basically, we talked about the safety angle and where automated vehicles really started pushing from the beginning, that if you've got 30,000, 35,000 fatalities, anything you can do with automated vehicle technologies to reduce that makes sense, even if they don't have any impact on traffic. If they just get rid of fatalities, it's worth it. What I want to focus a little bit today on the control side has more to do with the energy side. And so really picking up on this energy and sustainability thread, we should keep track of sort of where we are with vehicles and sustainability. Take a ballpark estimate from, I don't know, a year ago. More than 7.5 billion people on the planet, only about 1.3 billion cars on the planet. What that says to me is that there's still potential, huge growths in the number of vehicles that could be tolerated in countries throughout the world. If you look at countries like India and China, those countries have relatively few vehicles per 1,000 people in the country compared to a place like the United States, where there's, on the order of like 800 cars per 1,000 people. So if you just map world populations at the levels at which Americans have vehicles, you're looking at a huge growth in the number of vehicles that will eventually be on the roadway. And so with that comes all the challenges, in terms of the environment and in terms of the environmental impact that those vehicles may provide. That's not to say that cars are bad. Obviously, it provides access to goods and services. We made that point about how critical it is to be able to move not only people but goods as well. So just kind of keep those numbers in the back of your mind as you're thinking about sort of how much potential growth there could be for vehicles if we are not careful in how we unfold them. And thinking on the sustainability side about how those vehicles are powered in the U.S., the majority of our transportation system is powered by petroleum. And sadly, most of the energy that goes into powering a transportation system is lost. The energy use in the transportation system right now is about 21% efficient. That most of the energy that goes into powering our vehicles is lost as heat. And anything we can do to make those systems more efficient and use less fuel is obviously good. But it's also important to think about how we might change the type of fuel that we use. Just to give an idea in terms of what the potential angle on the fuel side is, obviously electrification of the vehicle fleet is one of the three super disruptive ideas in the transportation space, along with connected and automated vehicles in the shared economy. This video just shows an animation of the growth of electric vehicles over the last decade. And kind of the main takeaway that you should see is not the individual makes and models, but just the rapid acceleration of the number of electric vehicles that are being sold in the US. And that, helps provide some hope that as we think about the huge environmental load that moving goods and peoples incurs, that if we can electrify the fleet and then use cleaner sources to generate that electricity, obviously that's a good thing. And how does that benefit us? Well, the air quality is still a major challenge in most of the world. If you look at where people are living and who has air quality challenges, there's nearly a one-to-one correspondence. That 80% of the people in urban areas are living in communities that exceed, World Health Organization limits, and the transportation sector is responsible for that particulate matter that is being emitted. So getting rid of the fuel source or changing the fuel source and trying to be more efficient in terms of the energy that we are putting into our transportation system, it remains the name of the game. Okay, and why am I bringing this up? Well, again, as I think about what we can do with automated vehicles to change the transportation system, and what other levers we have as transportation engineers, one of the levers we have is policy. you look at where the cars are being sold right now, the leaders by volume are China, the US, and Norway. But if you look at the leaders in terms of percentage of vehicles that are sold, Norway is the standout. And it's a standout for a variety of reasons, but the main message is that the policy, most of the EV sales right now are still driven by policy. So getting the policy right to incentivize those vehicles being sold in the market remains, the name of the game. And so if I were being, maybe on a soapbox a little bit, I would say that it might even be worth thinking about, trying to put our energy and automation in the vehicles that are most likely to be electrified rather than in conventional vehicles. Let's target a little bit more in terms of where automation technology might actually impact energy consumption of the transportation system. This is from a recent survey in 2016, looking at some of the different technologies that might be impacted by vehicle automation, in particular, what they can do for the energy consumption. So you take a technology like vehicle platooning, where you have vehicles traveling very close together at high rates of speeds, exchanging information to achieve that close spacing at high speeds. That can significantly improve energy efficiency, and I'll talk a little bit about why that is later today. Eco-driving are concepts where you either change the route or change the driving behavior of the driver to reduce the amount of fuel that's consumed. Maybe the most naive version of this is just in your vehicle. If you have an option to switch the vehicle into an eco-driving mode, it'll accelerate and accelerate less aggressively and keep the vehicle running a little bit more fuel efficiently. It can get more exotic. You can choose your route through cities to not just minimize your travel time, but also to be less fuel consuming, with one category being things that you can actually do at traffic lights. And I'll say a little bit more about that as well.
We had a question, by the way, sorry to interrupt. We had a question. Are countries' policies driven by actual technology on electric infrastructure?
Boy, that is a great question that I'm not even going to attempt to answer. But what I can do is take that question offline and find an EV infrastructure expert and close the loop there.
Thanks.
Great question. No idea what the answer is. On the de-emphasized infrastructure or de-emphasized vehicle performance, this one I think is actually pretty interesting. Basically, the argument goes something like this: that if you're in the back of a vehicle and take it for a taxi today, like if the ride is smoother, you don't really care about the horsepower in the vehicle. If you basically can start using your time to do other things rather than driving and operating the vehicle, you might be less concerned about the horsepower to weight ratio. You might actually prefer de-emphasized performance in vehicles so that the rides are overall smoother. And that's really getting you out of the loop of trying to pass the angry driver in front of you and really becoming more like a passenger or more like a chauffeur. So there's other technologies that can play a role in reducing the energy consumption, but the ones that offset that are the possibility of having, basically cheaper travel, making it more convenient, allowing user groups that currently don't have access to vehicles, getting those folks access to vehicles. And all those things can offset those potential energy savings and actually increase energy consumption. So what we actually will see in the future is a mix of sort of how many of these features that can reduce energy consumption will balance out the ones that potentially can increase energy consumption. So the verdict is still out in terms of the automation technology of what the impact on energy consumption will be. In terms of the impact on traffic congestion, I mean, this is pretty much like Myth 101, that if you automate the vehicle fleet, that suddenly all of the traffic problems in your community will disappear. This was very important locally in my own community in Nashville, as we were thinking about whether or not we should invest in an $8 billion transit referendum to increase the amount of transit services in our community. And one of the pieces that came into the conversation was this question of like, well, automated vehicle technology is just around the corner. I've heard about it so frequently in the news that, there's no point in investing in this old technology like transit because we just won't need it. And I think that's a misnomer. One, obviously, because of the challenges that we're still facing with deploying vehicles that are automated, fully self-driving at scale. And two, because there are certain benefits that public transportation systems have that are going to be very challenging for automated vehicles to hit. So I'll say a few more words about that in a moment. But this big question about like, will automated vehicles cure congestion is again one of these trade-offs. It depends on the supply and demand. And on the demand side, we don't have exhaustive studies on people and their willingness to use automated vehicles in practice, in part because the brain off automated vehicles, level 5, are not widely available, even in the research demo space. So there was a study done by Joan Walker at Berkeley not too long ago that tried to come up with the next best thing. And the next best thing is like, well, what's the difference between an automated vehicle and a chauffeur? If you don't talk to the chauffeur and they don't talk to you, not much. You get in the back of the car, the chauffeur takes you where you want to go. And the chauffeur can do things that automated vehicles can do too. I don't really want to go to the airport and pick up, friends that are flying in or relatives. Why don't I just go have my chauffeur pick them up? Or make it more concrete. If you don't want to drop your kids off at school every day and pick them up, why don't you have the chauffeur go do that for you? In the future, the automated vehicle will do that for you. And these trips where, your car is leaving your driveway to go to pick up or drop off your kids at school, in the future won't have anybody in the car. So I constantly remind people that if you are frustrated in traffic today, imagine looking to the left and looking to the right and finding no one in the cars next to you. And that's totally possible when these so-called ghost trips, or the cars that have no one in them, are taking trips to go do stuff for people, even though the people aren't yet in the vehicle. Other things that came out in this study were that people want more travel. You make it more convenient. Why wouldn't people want more of it? I think the piece on the retirees is actually an interesting and important one. Retirees in this study, there are disclaimers at small sample size, but I think directionality wise, it's obviously in the right direction. Retirees took longer trips at night. Okay. Does that make sense? Absolutely. If you think about user groups that are, have potentially diminished capabilities to drive in terms of reaction times and otherwise, then, they're getting people access by automating those vehicles and allowing them to take those trips where they wouldn't previously do it is obviously a good thing. It's increasing access. But often in transportation, we sometimes confuse increasing mobility and increasing access. Increasing mobility means more vehicle miles traveled. Increasing access means getting to more things that I want. And you don't necessarily have to do that with more vehicle miles traveled. So automated vehicles can increase access. The trick is whether or not they're going to increase that access exclusively at the cost of increasing vehicle miles traveled, or if there are clever things that we can do via sharing or otherwise to get more access, but without necessarily proportional increase in vehicle miles traveled. The main takeaway here I want you to have is that automated vehicles, I'm confident, will increase the demand for travel, which can potentially cause more congestion if we can't increase the supply on our roadways. Well, can we increase the supply on our roadways is a natural question to ask. And the short answer is, obviously, yes, if you build more roads, but also if you change the way that cars drive. This idea of vehicle platooning is one in where vehicles that are close, very spaced together move at high rates of speeds, and the cars exchange information so that the vehicles can basically follow in this dense platoon of cars in a way that maintains uniform spacing and speed. Of course, this video is from several years ago from the Path Automated Highways demo, but we'll see later in the IPAM program, folks like Kalle Johansson's team at KTH have been working with Scania Trucking, putting a modern twist on these platooning technologies for the freight sector. The key idea here is that by putting these cars really close together and moving them at very high rates of speeds, you could effectively double or triple the capacity of the roadway in ideal settings. And so in practical terms, that means basically building a freeway on top of your existing freeway just by changing the technology inside the cars, not putting a single additional lane mile of asphalt on the roadway. And paving roadways and expanding them is a very, very expensive endeavor. So swapping out the vehicle technology and getting capacity increases instead is a natural and smart thing to do. Okay, but the key takeaway here is that you need to move these vehicles together at high rates of speeds, and I want to unpack that in just a little bit more detail. So drilling into some microscopic, remember micro, we refer to dynamics of the individual vehicles in the traffic stream. Some microscopic quantities could include for vehicle J, the speed of the car, VJ, the spacing, or more precisely the space gap, the front bumper to rear bumper distance between this vehicle J and the vehicle in front of it, vehicle J plus 1. I can look at the spacing, not the space gap SJ, but the spacing, which is the front bumper to front bumper distance. The spacing is not an important quantity if you're trying to control this following vehicle to avoid colliding with the rear bumper, but it is an important quantity to relate what's happening at the micro level to the macro quantities. So if I take this spacing, this is the distance basically from one front bumper to another, you can kind of view this as the space that one car occupies, space per car. And if I invert that, then I end up with something like car per space. And the car per space is exactly the density of traffic at a macroscopic level. So if we take the average spacing, we find that it's exactly 1 over the density and vice versa. I can also look at a quantity called the headway. That's how many seconds behind this lead car the following car is. So the way, in driver's education training, at least I learned, you find a point at which this car passes a marker on the roadway, and then you count 1 1,000, 2 1,000, and then you should be following that car, passing that same point in 2 seconds. That time separation of the vehicles is referred to as the headway. We can talk about the time gap, which, just like the spacing and the space gap, might refer to the time between the rear bumper of this car and the front bumper of your car. The key piece on the headway, though, is really this notion that, again, the inverse of the headway is the flow and vice versa. If I'm thinking about how many cars per time or time per car, those quantities are interchangeable. Okay, so I've got these microscopic quantities. What I want to do is I want to describe the dynamics of my vehicle. I'm going to look at its acceleration as some function of these microscopic quantities. I'm going to look at the spacing or the space gap, depending on the model. It's only obviously going to differ by the length of the car here. So I'll kind of use them interchangeably when context is relevant or context is obvious. So I'm going to accelerate or decelerate as some function of the spacing, some function of the relative velocity, whether I'm encroaching on the vehicle ahead or getting further behind, and some function of my own speed. At some point, if I'm driving at the speed limit, I stop caring what the car in front of me is doing. If it's far away, I'm going to drive according to the speed limit. There are a million ways to choose this functional form, and some good rational driving constraints that one might impose to make sure you do things like slow down when you're encroaching on the vehicle ahead and it's getting close. But for now, let's just suppose one model of a very simple form. It's called an optimal velocity model. What it does is it accelerates or decelerates the vehicle as some function proportional to this quantity alpha. It's just a parameter that looks at the difference between my speed, Vj, and my desired speed, which is a function of the spacing. So capital V here denotes my desired or optimal velocity. It's a function of my spacing. And I just look at, like, if I'm really close to the vehicle ahead, I might have a very low desired speed. I'll look at my current speed and I'll accelerate or decelerate accordingly at some rate controlled by alpha. Okay, so this controls my acceleration dynamics. And if I looked at what happens to these vehicles at equilibrium, basically when I'm not accelerating or decelerating, it's pretty easy to see that the velocity of my vehicle will exactly be the velocity of this optimal velocity function or desired velocity function. So really, it characterizes how I'd like to drive. Is exactly going to decide what the equilibrium of my driving looks like. Okay, so what do these optimal velocity functions look like? Just like in the macroscopic quantities, we have a million different ways to describe fundamental diagrams. One can choose similar functional forms for the microscopic optimal velocity function. I'm choosing what has to be one of the simplest possible optimal velocity functions. Here's what it looks like. When my spacing is very small, say delta x min, the minimum spacing I'll accept, my desired velocity is 0 miles per hour. But as the spacing between my vehicle and the vehicle in front continues to increase, I'm willing to drive at a higher speed. Up to a point where I reach some critical spacing. Once I hit that critical spacing, I'm willing to drive at the speed limit. And if you continue to increase my spacing, there's fewer and the car in front of me is further and further away, I'm still going to drive at the maximum speed. Okay, so that's a very simple optimal velocity model. It takes me linearly from zero velocity to Vmax as a function of how close I am to the vehicle ahead. And you can, of course, write this down in a mathematical form. I'm not going to go into too much detail other than to flag, if you're reading this carefully, this linear portion of the optimal velocity function has some funny parameter W on here. This W has a negative sign, and I'll explain in more detail what that is in future slides. Okay, so there's an optimal velocity model. What I'd like to do is now translate that to the macroscopic quantities. Remember, vehicles only operate at this optimal velocity function in this example when they are at equilibrium. But okay, let's suppose they are. So I'm on this curve. Well, if I've got a bunch of vehicles that are doing the exact same thing, then I can invert these spacings to get densities, and instead plot the velocity of the traffic overall as a function of the density of traffic. And when I invert this spacing velocity curve, invert the density, let me be more precise, invert the spacing to get the density and then replot the speed as a function of the density, I get something that looks like this. At low densities, at high spacings, I travel Vmax. But after I hit the critical density, which corresponds with the critical spacing, they're just inverses of each other, then I start to decrease my speed at a rate 1 over the density, 1 over the density, until I hit this jam density point, which exactly corresponds to the inverse of the minimum spacing. This velocity curve, which has a constant portion and then a portion that grows at a rate 1 over rho. If I multiply that velocity function by the density again, then I get a fundamental diagram, the flow as a function of the density. And in this case, with this simple optimal velocity model, we get all of the traffic states that come from a triangular fundamental diagram. At light densities, adding more cars onto the roadway increases the flow, increases the throughput of the roadway. Why? Because you're basically in this region where the density and the speed are not changing. You're in this region here where the density and the speed, you change the density, but the speed is not changing. You change the spacing, but the speed is not changing. The cars are far apart, so you can add more cars on the roadway without changing the speed at which they drive. Well, then increasing the throughput is straightforward. Add more cars on the roadway, and you will get a higher density. They'll all still be traveling at the same speed Vmax, and the flow will increase on the roadway. But again, once you hit that critical density corresponding with the critical spacing, you start adding more cars on the roadway, you're chopping into that spacing between the vehicles. Now the cars want to drive slower, and as a consequence, the flow starts to decrease. Okay, the rate in the fundamental diagram, the slope of this congested part of the diagram, I've defined as W. That quantity is the maximum backwards propagating shock wave speed. If you're running with an LWR, scalar conservation law in the background here, basically this slope speed here denotes the rate at which the back of a queue grows when you've completely stopped the outflow and you're just jamming in vehicles into the queue, into the QUEUE, the queue, as fast as you possibly can. Then the shock wave on the back of the roadway will grow at a speed W. Of course, that speed is negative because the shock wave is growing against the flow of traffic. Okay, so that W there still finds its way into this optimal velocity function at the micro scale. But I also want to point out and just reiterate one more time that all the points that are corresponding on this fundamental diagram are based off of the fact that we're assuming that all these vehicles that are driving with this optimal velocity function are at equilibrium. Okay, so just kind of leave that on the side. Okay, so what I've tried to convince you is that there is a relationship between what's happening at the micro scale and what's happening at the macro scale. Now we can start to ask what happens if you modify that through vehicle automation. And so I've got two different optimal velocity functions. We start initially with one that's kind of out of this, I guess it's almost like a light blue color. Suppose that's what humans do, okay? And then I can modify what the humans are doing by overwriting the cars with vehicle automation. And the vehicle automation can either follow this red curve or follow this one. What's the difference between the two curves? Well, in the figure on the left, what we've done is we've pushed this critical density, the critical spacing further to the right, meaning I will drive at my maximum speed for larger spacings, but as soon as you start encroaching into that critical spacing, I'm going to start slowing down. Where humans might still be willing to operate at the maximum speed, I want to start slowing down based on my vehicle automation system. On the figure on the right, you can see for every speed that the human would accept given a spacing, there's an automated vehicle that wants to drive faster. Or said differently, for a fixed speed, the automated vehicle will accept a smaller spacing than what the humans will. Well, this gets at its core exactly to what the platooning vehicles are trying to do. If you drive at a lower spacing for the same speed, you've got more cars on the roadway, the throughput will increase. And you can see it when you take these optimal velocity functions, the ones that are bad for capacity and the ones that are good for capacity. You take what's happening at the scale of the vehicle, you look at what happens to the density overall when all the vehicles are driving at that equilibrium condition, and you see that when you get back into the flow density space, these choices of slowing down at larger spacings result in things like a lower maximum flow possible on the roadway, a lower capacity of the roadway. Whereas if you're willing to drive at a maximum speed longer, willing to drive at a maximum speed for smaller and smaller spacings, you end up with a fundamental diagram that has a much higher capacity than what the capacity of the humans will. So what it really boils down to is the designs of what these vehicle automation systems do at a local level will influence what happens at a macroscopic scale. And if you're platooning, you have the possibility of putting a lot of cars close together at high rates of speed, and you can do things like significantly increase the number of vehicles that can be served per lane in a given hour of the roadway. Okay, so these are of course exaggerated models, and these depend on how the systems are practically designed, but I hope to convince you that, again, things that you do at the micro scale of individual vehicles will influence how many vehicles you can actually serve on the roadway. Tying things all the way back to the very beginning, it's one thing to talk about, densities of vehicles and flow of vehicles. It's another to talk about density of people and flow of people. If you change the definition of the system goal to one, instead of maximizing vehicles per hour on the roadway and instead maximizing people per hour on the roadway, you can get pretty spectacular technology improvements by doing things like carpooling. That alone, if everyone would carpool, would practically double the people throughput of a lane of roadway. You could take it from on the order of 2,000 vehicles per hour, 2,000 people per hour in single occupancy vehicles, to still 2,000 vehicles per hour, but 4,000 people per hour if you're carpooling. Yes, and carpools work with more than just two people. You could put 4 people in the car, and now you're talking about building freeways on top of freeways on top of freeways on top of your existing freeway. 4x the capacity if everybody picked up more people. So one can imagine that there's a lot of interest in using technology to figure out how to actually convince people to do this, how to align the routes to make it not so painful for people to do things like carpooling. This was most famously pointed out in the transportation planning community by these iconic photographs in Munster in the early 90s. You look at the space that people take up when they're on bikes versus cars versus a bus, and it's pretty clear that the bus is the people per square foot winner in terms of density compared to the car. And yes, if you automate the vehicles, they still take up the same space unless you do fundamental redesign of the vehicles that don't look like this any longer. They need to be narrower, they need to be shorter, they need to occupy a lot less space if you're going to get any benefits from automating them in terms of the space that they occupy. Well, moving into the urban grid, where is the space most sensitive? Well, obviously it's at the intersections in urban networks. That is the high rent space in cities. Why are the intersections so important? Well, the intersections are important because those are the bottlenecks. You've got vehicles that are coming from multiple directions that all need the same space. I can't serve vehicles from this direction in this space and vehicles in this direction if those vehicles need the same space at the same amount of time. So I might have plenty of throughput on individual branches going into the intersection, but the intersection just has a finite amount of space available for it. And so this question about how to jam as many people through the intersection becomes the crux of what people are trying to do. maybe the most exotic version of how to improve the use of that space comes from some technologies that were pioneered by a team at University of Texas, Austin.
Autonomous Intersection Management.
I'll just play the video.
Traffic Control for the Future, a project from the University of Texas at Austin. Most intersections today are controlled by traffic signals, stop signs, or roundabouts. However, even when people do follow these protocols, intersections are the source of much traffic congestion and many accidents. Even though they take up a small percentage of the roadways, roughly 1/4 of all accidents and 1/3 of all fatal accidents occur at intersections. It is now apparent that autonomous cars are well on their way to becoming a reality. At first, they will need to follow the same intersection control protocols that were designed for people. But this project considers, once most cars on the road are autonomous, whether we can do better than that by way of an AI-based coordination mechanism. In this research, we introduce a new multi-agent intersection control scheme specifically designed for autonomous vehicles.
So you see in the video, I mean, this continues, but the crux of the argument is that basically in light traffic conditions, this space is not very efficiently used because you've got people from multiple directions that all want to use that space in the intersection, but you cannot safely, as humans, have cars moving in all directions, right? So if you make the cars connected and automated, they have the possibility of doing things like reserving the space and the time at which they need it to chart a pathway through the intersection. And as long as that path is conflict-free with other vehicles that have reserved paths through the intersection, then you can serve vehicles coming from multiple directions simultaneously. Obviously, the challenges of doing this on a real freeway or on a real urban network today would be that, one, if every vehicle is not automated, this becomes something that won't work, right? Because you potentially need very, very low tolerances in terms of making sure you get to your reserved space at your reserved time. If you show up late or show up early, you might be interfering with someone else's reservation, i.e. colliding with that person. There's been a number of issues that have been raised for other road users as well. So if you try to operate these intersections and then you need to walk a pedestrian across that intersection, that becomes extremely challenging. I think where the more interesting research is being done today is at trying to figure out things like, well, if you have a network of intersections like this, what happens to those networks, especially as the flow rates become large? In the extreme case, once you have, this type of technology will allow you to use the intersection if it is possible to serve all the demands from all the directions. But at some point, if the demands are too high, then you still need to essentially batch the vehicles and send them through. So a lot of different teams right now are working on the technologies to try to take these, I think, relatively provocative ideas and figure out how they might actually work in a real environment, not just in light traffic conditions, but in heavier traffic conditions and at large scales, and at when these systems are with mixed automated vehicles and human-driven ones. I think there's other exciting technologies that are happening on the control side at traffic signals that don't require all the vehicles to be connected and automated, but just a special category of those vehicles. There were some recent experiments that were done in the last year to look at technologies that might benefit the freight side on the trucking. And the idea here would be that you have intersections. The traffic signal control unit knows its timing. That sometimes is referred to as signal phase and timing information. And if I were able to pass that information to the vehicle, then the vehicle, either via automation or via a human driver, might be able to use that information to speed up or slow down to not race up to the traffic light and stop. And so one of the examples that's shown in the plot below is based out of some field experiments that were run. On the x-axis, we have the time in seconds. We have a green phase that then turns to amber and then red before switching to green again. And in the baseline case, if the truck does not have information, the truck is traveling at a speed, realizes the light is changing, slows down, stops, waits for the light to turn green, and then can accelerate again. But if you have this signal timing information in advance, the truck can make a small adjustment in its speed, actually make it through the light, make it through this position x equals 0, make it through the light before the light has changed, and continue on its pathway. And if you think about a fully loaded truck, obviously being able to slightly accelerate, burn a little bit of energy, but avoid having to bring that weight to a complete stop and then accelerating it again from a full stop can certainly benefit you energy-wise. Now, the tricks, of course, are that you can't always accelerate if there are cars ahead of you. You can't accelerate if you're going to violate the speed limit and so on. There are also similar problems on the deceleration side. You might want to take your truck and rather than coasting up to the light only to have it suddenly change on you, if you know in advance, you can start gracefully reducing your speed and maybe even time it so that by the time you arrive at the intersection again, the light has turned green. This type of work does matter in low flow conditions and can reduce the energy consumption of those trucks by anywhere between 4 and 9%. So another way to use connectivity, this is not without automation, these numbers, just connectivity, knowing that information ahead of time that could actually have a measurable impact in terms of the fuel efficiency of freight. The platooning angle, which I hinted at before, we made the argument about how you can do connected technology to increase throughput. But I would postulate the following question. Do trucking companies actually care about throughput? It depends. I think as trucking companies occupy larger and larger shares of the fleet, then certainly they do care, right? Like if you think about all the Sprinter vans that run around in our neighborhoods, they might be approaching a level where the interactions between the different vehicles could have some effect. It's a postulation. It's not an actual quantitative statement. But I would argue that in general, if I were running a trucking company today, personally, I would be less concerned about overall throughput of the roadway, and so would not be adopting connected technologies for throughput. But I absolutely would care about my operating cost in terms of my fuel. Trucking companies might lose on the order of a third of their cost to fuel. And so if you can reduce the fuel consumed by the truck, that's obviously directly in their financial and their environmental benefit. And so by putting these trucks close together, the kind of clever thing is that you can actually reduce the amount of fuel consumed by the platoon of vehicles. And the high-level idea is that when you put these trucks closer together, you can actually reduce the pressure in front of the following vehicle. And that reduction in pressure can actually help reduce the aerodynamic drag on that vehicle, causing it to be more fuel efficient. So there's been a number of studies that have looked both experimentally and theoretically about what these consequences for truck platooning might look like. But here's an example where basically, depending on how close you operate the following truck, the fuel savings of the following vehicle can be upwards of 20%. And the leading vehicle itself can also get a boost, mostly because of the fact that the pressure drop behind the truck is not as extreme. So purely from a fuel perspective, truck platooning makes sense. And that's why we're seeing a huge number of trucking companies that are aggressively working on these types of technologies. If you're able to automate the truck platooning in a way that you can also eliminate the driver, you can hit right on another pain point for fleet operations, which is another big operating cost is the cost of the driver itself. So I think connected and automated vehicle technology, purely from a vehicle perspective, does have a lot of benefits that gets folks excited on the freight side. I want to now pivot to a little bit more discussion about what can be done on the bulk traffic control side. We saw this pivot in part one of the tutorial about how classic sensing has been, in some cases, especially in the consumer market, replaced by sensing that is done by the vehicles themselves, either through level 1 automation systems or more commonly today through GPS devices that are in those vehicles. I also want to talk a little bit about what's happening on the traffic control side. Especially on the freeway side, we are, still today working on deploying lots of infrastructure to better regulate freeway control and what that might look like on the vehicle automation side in terms of how we might be able to leverage those control technologies in the vehicles to start using the vehicles themselves as actuators. I want to give you a glimpse of what today's so-called integrated corridor management systems look like. This is a video that is created by the Tennessee Department of Transportation on a $100 million project that is going on right now, where they are doing things like realigning some of the entrance ramps, installing meters to regulate the inflow rates onto the freeway, deploying overhead gantries that have messages that let you know that a lane might be blocked ahead due to a crash, and try to alert the motorist to move. There are also boards that will help drivers decide whether or not they should take a detour route. And then if the detour routes are activated, they will be updating the signal timings on the parallel surface streets to be able to ship some of that throughput from the freeway onto the surface streets. This notion of an integrated corridor management system really ties to the idea that there is both a roadway on the that has signalized intersections on it that runs parallel to the freeway, and I want to use all of the capacity of that corridor together. And importantly, on the freeway side, that means putting more infrastructure down to throttle the freeway, in particular through these ramp meters and through the gantries. Okay, so how does ramp metering work? Well, I want to give just a couple ideas of why people would ever do something like regulate the number of cars that are entering on the freeway that might benefit motorists overall. To see the ramp metering angle, the one common assumption that we make is that the fundamental diagram that describes the traffic states that we can see on the freeway has a capacity drop, that in free-flowing conditions or uncongested densities, you stack more cars on the roadway and the throughput continues to increase up to some queue capacity. But once you enter into a congested state on the other half of the diagram, you end up on a different branch that has even as you reduce the number of cars on the roadway, get closer to that critical density, it still has a lower total outflow than what you can get if you're on the free flow branch. So sometimes this Q con would be the capacity and congestion. Okay, basically this assumption makes it impossible to realize the capacity of the network once congestion has been set in. So you don't want congestion on your roadways. Here's an example of what this could look like. So I have two roadways, one in which there is no control at the ramp meter, because the total inflow from the upstream and the ramps is large enough that I induce a merge point here and congestion sets in. Once I've got congestion set in here, I will never be able to get an outflow rate which exceeds this reduced outflow Q con. If I was able to regulate the flow at the ramp or using overhead signs that might also allow me some control on the main line, if I were able to reduce the total inflow enough to switch the shock wave speed, instead of one shock wave that is growing, instead it reduces. If it reduces and eliminates that congestion zone, I could get back onto the uncongested branch of the fundamental diagram and then throttle my inflow on the ramps and possibly upstream such that I reach this maximum outflow rate. And again, maximizing the outflow rate, I won't detail it here, but in many cases corresponds to minimizing the travel time in the network. So the idea here is that even though I've forced some folks to wait here on the network, what I'm able to do is get this maximum outflow rate on my network. And that's an artifact of this modeling choice where I have a capacity drop in the system. And maybe to say it a little bit stronger, there's a lot of growing empirical evidence that says that this could be anywhere between 5 and call it 15% gap between the capacity and free flow and that in congestion. But even if you don't subscribe to the capacity drop argument, there's still reasons to do ramp metering. A reason that you might do that is if you have outflow that is not just outflow at the edge of the ramp down, or the edge of the main line here. If you have another exit ramp, clearly it's not a good thing if you have congestion back propagate so far that vehicles that want to exit here are inhibited and incur some delay in exiting out here. So if I'm able to, again, throttle my rate at which I enter vehicles in, and instead of seeing the congested state appear, I keep it free flowing, then the outflow rate here in here, they're both the same, but I'm not having reduced speeds back here that block vehicles from exiting on this ramp. Okay, so the ramp metering ideas have been around for quite some period of time. There's a nice review article in 2002 that goes into quite a bit of detail about how to set up these networks and the basics of ramp metering. Where the connected and automated vehicle world is getting to is ideas where you might, instead of having to use ramp meters or messages overhead that change the speed to try to change the inflow rate upstream, you might use the vehicles themselves to reduce the flow into bottlenecks, letting them clear, and ultimately getting either the exit ramps unblocked or avoiding the capacity drop on the outflow. And I'm sure in the course of the IPAM program, we will see quite a few talks on exactly how people are using automated vehicles to do like a newer variation of ramp metering and variable speed limit control. I also want to look at another example of what you can do with automated vehicles, specifically on the roadways, changing the fundamental physics of the flow. We've seen in a couple of different tutorial lectures the famous Sugiyama experiments where you have a bunch of vehicles, they drive in a track. All of these vehicles are under human control. And because of the nature of human driving, we see small perturbations in the flow get amplified to the point where some vehicles at some point on the track come to a complete stop. These same vehicles then race around to the other side of the track only to get stuck in congestion again. And these so-called phantom traffic jams are actually a result of the unstable nature of how humans drive. And even if only a subset of the vehicles have vehicle automation, if those vehicle automation systems are designed in the right way, we can potentially change the emergent phenomena of this flow, eliminating these phantom jams. So these phantom jams are ultimately a result of unstable traffic. What happens ultimately is that if you look at vehicles driving along the roadway and plot their spacing as a function of time, these vehicles have some bump in their spacing. It could be anything from a driver who is reacting to a vehicle ahead. It could be something like a disturbance in the geometry. There's a hill, and so the vehicle spacing changes slightly. As the vehicle following that lead vehicle sees that the spacing is changing, they also potentially their speed, they adjust their speed and try to accommodate the perturbation that the lead vehicle had. But if they react too late, they must overcorrect to maintain their spacing and avoid a collision. Well, the vehicle behind them does the same thing. By the time they see that there's a disturbance, they have to overcorrect, thereby amplifying the perturbation. Of course, they get back to their equilibrium state, but not before passing that disturbance onto the vehicle behind, which continues to amplify the disturbance. In a string stable traffic flow, those disturbances, rather than amplifying as they pass back in the platoon, are instead reduced. So these string unstable traffic features end up resulting in features in the flow that we definitely don't want. This is a plot of the time-space diagram from the Sugiyama ring experiment. You have the position of the vehicles along the ring as a function of time. Vehicles that exit the top of the ring basically then find themselves back at the bottom spot and continue to wrap around. Initially, the flow is relatively smooth, but you see something happening here where a gap initially opens up. This vehicle starts to accelerate, but not before these two vehicles get rather close together. Those vehicles start to interact and decelerate. The vehicles behind amplify that disturbance to the point where these vehicles are now slowing down and then speeding up, slowing down and then speeding up. Well, that slowing down starts to get a little bit sharper and sharper as it goes back through the platoon until you get to points like here, where these vehicles have virtually come to a complete standstill before they accelerate again. This wave that is growing wraps around around the ring to the point where here you can see these vehicles are now coming to a virtual standstill before they accelerate again. And these waves continue back in the flow, wrapping around, and they have well-defined speeds that can be reproduced by microscopic models that have been chosen in such a way that they have string unstable driving behavior. these features of these instabilities are not just things that happen on individual ring tracks, and they're not features strictly of the wraparound, but they also happen on open roadways. Here is a video from a freeway in Georgia that has one of these characteristic phantom jams. So you just see as the flow is moving forward, at some point, vehicles slow down, and the pocket of slowing down vehicles moves against the flow. Here, you can see another one forming right here as it moves its way back against the flow of traffic, and there's just a pocket of stopped vehicles that are stopped because the vehicles in front of them are slowing down. That is a phantom jam. There's no obvious cause for it, but it's actually due to the way that the humans are driving. So if these jams are features of the car following dynamics of humans, then if we modify the car following dynamics of humans, we might be able to change that emergent feature of the flow. To set that piece up in a bit more detail, I'll again look at the microscopic behavior of the drivers. I'll look at the acceleration of vehicle J as some function of its space gap, its relative speed, and the speed of the vehicle in front. I put a bunch of these vehicles on a ring, and then I can describe each of these vehicles as a n-car state with two n-dimensional variables. Basically, I'll keep track of the position and the speed of every vehicle, and I can recopy these velocity dynamics for every single vehicle until I have a system that describes the dynamics of all of the states and all of the speeds of the vehicles. Again, the key piece here is that there's no connectivity, there's no automation. Literally, the dynamic of this vehicle is governed by the vehicle in front of it. The dynamics of this vehicle are based on the speed and spacing and relative speeds to the vehicle ahead of it. And once we have the end system dynamics, we can modify these vehicles to change the dynamics and ultimately stabilize the traffic. So we modify one vehicle, and instead of having it drive like a human, here's a specific form of what a human could do. A human might do something like an optimal velocity model we talked about earlier in the tutorial, plus some term that explicitly relaxes you to the lead vehicle velocity, scaled with the spacing. So the closer you are to the vehicle ahead, the more you want to drive according to that vehicle speed. Humans could very naturally drive in a way that they relax to the desired velocity of their own optimal velocity function and to the leader velocity. But since it's an automated vehicle, we might also, for a single automated vehicle, we might add an extra term in it that makes it drive like humans do, but with a modification that I'm going to try to also have that vehicle relax to some stabilizing velocity UEQ. Okay, so if I do that, then I can basically take my system, linearize it, and choose the parameters of my controller such that I can stabilize the overall system. You saw in Benny Seibold's tutorial from last week this discussion about how to actually stabilize the ring in quite a bit more mathematical detail. For where we are today, it's just important to know that one can design these stabilizing controllers, and indeed, when you put them on a track in a ring, even with one automated vehicle, you are able to stabilize the ring. Right now in the video, both of these rings are running with a stop and go wave on them. As the video on the right continues, you can activate the single blue car that runs a stabilizing controller, and basically before your very eyes, magically that vehicle has stabilized the ring. It happens that this vehicle is running a control algorithm that on the very first pass is able to consume that traffic jam. But the core ideas of what that vehicle is doing essentially boil down to traveling the same distance as the vehicle ahead of it in the same amount of time as the vehicle ahead of it, but it does it according to the average speed of the vehicle ahead rather than this highly volatile speed up and slow down. And that's a bit of a hand-wavy interpretation of what's happening, but I think it gets it a little bit closer to intuitively why something so magical can occur. Those vehicles are getting to the same spot in the same amount of time, but just doing it with a more uniform speed profile rather than driving too fast and then too slow again. The key thing that we've been fortunate to have a number of collaborators that are part of the IPAM program work on is really this idea that it doesn't just have to work in simulation, but it can also work in the real world. So following our first tutorial from Jonathan Sprinkle earlier today, talking about a lot of the challenges of getting a car to do what you want. If you can get the car to do what you want, then you can do things like design controllers that can do things that don't only prevent collisions, but also benefit the traffic flow overall. So we saw in this video initially the stop and go waves, just as we saw in the Sugiyama video, while the car was under complete human control. Then an automated vehicle controller is triggered that is specifically trying to smooth out that jam, effectively acting like a pace vehicle, reducing the overall speed volatility on the ring to the fuel benefit of all the vehicles on the track. I think what's most important about what's happening in this video is the fact that one vehicle can have such a dramatic positive benefit on the overall flow. This stop and go driving is bad for a number of reasons, not just in terms of being annoying, but it's really bad for fuel consumption. So if you look at the same type of time-space diagram that we saw with the Sugiyama plot, here it is repeated for the video I just showed. The red trace here is the trajectory of the automated vehicle, initially under human control. And then where this blue vertical line is, this is where we start actually triggering a controller to dissipate the wave. Initially, relatively uniform flow, but humans do what they do. Eventually, you get the stop and go wave. By triggering the automated vehicle, we basically allow some gaps to open up so that we can drive a more uniform speed. And that more uniform speed passes on its benefits to all the vehicles that follow immediately behind. By actuating that control and comparing the period where the stop and go waves are present to where the traffic flow is much more smooth, we can see fuel consumption reductions measured by all of the vehicles on the track through their OBD2 ports in upwards of 42%. So that's comparing, again, probably the most extreme bad driving you can do, speeding up and slowing down, to a relatively smooth flow. But again, this is, I think what's intriguing is that it's one car that's giving fuel benefits to all of the other vehicles that are on the track, not only itself. And that's something that I think really is not possible to do today if you're only using fixed infrastructure to do the control. I can actually say a little bit more about that. I think it's with today's roadside infrastructure sensing technologies, most of the data we're getting, as I talked about in the first part of this tutorial, is mostly aggregate data. You get 30-second counts or 5-minute counts and average speeds. So you don't even, you can't even easily tell whether or not these stop and go waves are present. And then these waves are relatively tightly located in space and time. So you need very precise information to be able to try to impact these flows in a meaningful way. And so by actually operating at the level of the individual vehicle, it provides an opportunity to change some features of the traffic flow, which I think are going to be extremely challenging to do if you only are looking at using roadside infrastructure and don't exploit the vehicles themselves as controllers. I want to take the time that we have left and just tie a few more ideas together in terms of where the current state of vehicle automation systems are. We often talk about these SAE designated levels of automation, where you take cars that have no driver assist capabilities, no automation. You are responsible for steering, you are responsible for braking, you're responsible for monitoring the environment, and you need to intervene. I mean, this is every car I've ever owned is in the no automation space. But increasingly, we're seeing cars coming out with either partial automation that can both simultaneously steer and accelerate and decelerate. These would be things like the Cadillac Super Cruise or Tesla's, I guess, infamously named autopilot system. But most of the car companies today are also offering at least some kind of driver assistance feature, whether it's adaptive cruise control or lane departure assist. These features would do things like, compared to my normal cruise control system on my car, which does its best to maintain 30 miles an hour or 50 miles an hour in spite of all the disturbances that might be happening in the environment, like hills, adaptive cruise control will adjust your speed additionally in response to the vehicle ahead so that you don't collide with it. The car ahead starts slowing down, you'll start matching the speed of that vehicle ahead. So the driver assistance systems are actually here today. If you look at the best-selling cars in America, most of them have at least level 1 automation capabilities, either as a standard feature or an optional one. And so those adaptive cruise control systems, which are one of the most common level 1 automation systems that are on these vehicles, are already there and already taking over some of the driving tasks from humans and potentially impacting the flow. And so it's interesting to ask, what kind of time headways do these cars follow with? Tying it back to those optimal velocity functions I showed you at the beginning of the tutorial, are these cars driving with shorter spacings at the same speed that humans do, or larger ones? If they're driving at shorter spacings, that potentially can improve the overall throughput of the roadway. And if they're driving at larger ones, it's going to reduce the throughput of the roadway. In terms of the flow stability, if the driving dynamics of those adaptive cruise control systems are stable, they might be able to smooth out some of the perturbations that are put in by humans. If they're not stable and maybe even amplify the perturbations worse than humans, they could end up making traffic worse when they're turned on. And these are features that are, features not, they are dealt with at the level of the individual vehicle design, but they manifest themselves in properties to the overall traffic that traffic engineers absolutely do care about. And the big distinction between technologies like this today and what traffic control engineers have had in the past is that, if you are the state DOT, you can do things like change the timing of your ramp metering controllers. It's much harder, and I would argue not done today, possible for the state DOTs to modify the dynamics of the control system that were put on the vehicle when they were sold and rolled off of the showroom floor. So it's one of this kind of new era ideas where, the vehicles are starting to impact the flow, and control it, but in ways that are not there at the level of the integration with the rest of the control system. I think over time that will change, but it's definitely getting towards where things are focused now more on the state of research. So what do we actually know about these low-level vehicle automation systems, in particular with the adaptive cruise control systems? Well, I think an important point here is that pretty much as soon as people started looking at human car following dynamics in the late 50s and early 60s, they were trying to figure out what kind of ordinary differential equations would make sense to characterize the way that humans drive. They almost immediately started asking questions about whether or not those car following dynamics were something like string stable or not. In the controls community, people were very interested in thinking about, well, what could happen if we automated those vehicles? And as those vehicles, people were looking at ways to automate them, it became very clear that if you try to use only local sensing information, like what an adaptive cruise control system would do, you've got a radar, it might tell you about the distance to the vehicle ahead, relative speed information, things like this. If you try to control the platoon without connectivity, using only that local information, and maintain what's called a rigid platoon formation, not allowing the platoon to expand and contract, but maintaining a constant spacing, you cannot design those vehicles to be string stable with a constant spacing. The right way to design those controllers using only local information to maintain string stability is to, instead of trying to maintain a fixed spacing in the platoon with no connectivity, maintain instead a constant time headway with no connectivity. So if you design the controller of the vehicle to do things like maintain a 2-second following headway, you can do that and choose the parameters of the controller to design those ACC systems so that they are string stable. Of course, we've also been doing quite a bit of work in terms of, since, in the 90s, the number of ACC systems that were commercially available was, I believe, 0. A lot of folks have been looking at what one could do in simulation to understand the potential benefits that these vehicles would have to the overall traffic flow. And these have also explored ideas that might also add in connectivity and look at what happens when in mixed environments, subsets of the vehicles can communicate with each other to try to regulate the flow. But until, say, the last 18 months, there's been relatively little information about how the commercial automation systems that were shown could be designed to be string stable in the 90s have actually been commercially deployed. And so in partnership with quite a few folks that are on the call today and also part of the long program organization, we started asking that question, what the commercial cars are practically capable of doing. And one way to find out if commercially available cars are string stable is to just rent a bunch of them, put them on the roadway, form a platoon. An important distinction here, these cars are not connecting with each other. They're just using local sensing on the following vehicle to measure spacing information and relative velocity information. Build a platoon of those vehicles, take your favorite signal generator, another vehicle, slow it down and speed it up and see what happens to the platoon. Does it dissipate the perturbation or does it amplify them? I think, running experiments is a useful construct, but it's filled with nuances. And in particular, if we're not careful in how we design the perturbation for this lead vehicle, one could very easily perturb the platoon, observe that the perturbation is dissipated through the platoon, and show existence that there is a perturbation that is dissipated. That does not imply that all perturbations will be dissipated, which is what we want if we're claiming that a car is string stable. So in other words, the only one, unless you're going to do a very careful experimental design, what you're really hoping for when you run these types of platoon experiments is a platoon that shows an instability, because existence of that instability is enough to declare the vehicles as string unstable. So here's the general setup. We've got a lead vehicle followed by a bunch of commercially available ACC systems that run those stock controllers. And we're going to take a lead vehicle and basically bump the speed, slow it down just a little bit, and watch what happens to the speed profiles of all the following vehicles. So all the vehicles are initially at 50 miles per hour. That is the University of Arizona CAT vehicle hidden in the blurred background. And actually, half of the folks on the IPAM call were actually drivers in this experiment. The lead vehicle slows down. The following vehicles slow down in response to the vehicle ahead. But because they slow down a little bit too late, they have to slow down a little bit further than the car in front. And very quickly, this sort of accordion effect that happens through the platoon causes this last vehicle to slow down so much that it's actually below the minimum operating speed of the adaptive cruise control system. And so that vehicle disengaged the ACC, handed control back over to the human driver, who pulled the vehicle off to the side of the road. So this kind of growing speed perturbation back through the platoon is a signature of this instability in the traffic flow that we'd like to avoid. We'd like these stock ACC systems to be able to dissipate some of the perturbations that humans have potentially put in the flow. But at least these stock ACC systems tested in this vehicle, in this experiment, were shown to not smooth the flow. They can actually amplify perturbations. Well, we didn't want to basically set up platoon experiments for every possible vehicle that we could get our hands on. Another way to test the string stability is to actually use models and analyze the models that are fit to data. So what we did is basically collected a bunch of data from additional vehicles where we have a lead vehicle that acts as a signal generator. The following vehicle runs a stock ACC system, and then we watch what happens to the stock vehicle, how it's driving, and we build a car following model of this vehicle under that ACC controller and basically use the data to infer the parameters of the vehicle under the control. So we assume that the vehicle accelerates and decelerates to relax to a constant time headway, tau. That could be like the 2-second rule or the 1.5-second rule or 3-second rule, depending on how the stock system is set up, and also relaxes to the lead vehicle velocity. So the parameters K1 and K2 just determine the rates at which you're relaxing to the constant time headway and the leader's velocity. When you look at these models with these parameters that are chosen empirically from the data, one can check to see if they're string stable or not by computing a property lambda 2, which more or less boils down to a question of whether or not the Bode plot is increasing or decreasing. And essentially, if it's increasing, there's some rich theory that's described in this Wilson and Ward paper that basically shows you that you're guaranteed to have some frequency at which perturbations are amplified. Whereas if this quantity lambda 2 is negative, it means that all frequencies you are dissipating the perturbations. For this simple model, because it's linear, we can calculate this condition that determines the string stability using only the parameters that we're estimating from the model. Okay, so again, by choosing the different parameters, we can see in simulation if the parameters are chosen to be unstable, string unstable, that the spacing perturbations grow, the speed perturbations grow as you go further back in the platoon. And if the parameters are stable, this is that same model just chosen with different parameters. The spacings do not amplify, and neither do the speeds. So it is possible for the model to be string unstable or string stable. And then we go and collect the data from a bunch of experiments, and we were able to confirm that all the vehicles that we've been able to test so far are in fact string unstable. And that's bad because basically, it's theoretically possible to design those vehicles to be string stable, and yet no commercially available vehicle that we've been able to test or that I've seen tested in the literature that is growing now has come back and shown anything that indicates that the vehicles could be string stable. Of course, all the analysis that we've done, with the exception of the platoon experiment, have been based on models. And so a basic question one could ask is like, well, how are we confident that the models are correct? And the way that we've been kind of checking this is by first calibrating our model to minimize the prediction error with the data that we collect. And then we find that under the parameters that make the dynamics that best fit the trajectories that we measure, we find that these vehicles are string unstable. What we can then do is go recalibrate the model, but with an added constraint that I'd like to find a new set of parameters that are not unstable, but that would actually result in a model that is string stable. And we can compare how well this string stable model fits our data compared to the string unstable model. And what we find is that one would have to significantly increase the error in the quality of fit in order to find a set of parameters that would make this model string stable. That somehow gives us confidence that as we are making conjectures about what happens to these vehicles as a feature of the model, that we're not running into problems of parameter identifiability that are changing, potentially the answer in terms of the string stability. Okay, so where does this put us? What I've tried to show you today is a mapping from the big picture problems in vehicle control that automated vehicles might be able to tackle and what they can't, right? Like vehicle electrification is a good idea no matter what. Policies that prevent rapid explosion in the number of vehicles that are on the roadway are things that we're going to need no matter what. But vehicle automation has a lot to potentially do in terms of reducing the fuel consumption of vehicles as they enter intersections, potentially the fuel consumption of overall traffic flow on freeways if we're able to eliminate these phantom traffic jams. But the current systems that are available today, these level 1 vehicle automation systems, we're learning more about them, and what we're learning so far is indicating that they alone will not be able to remove all the phantom traffic jams that show up on the freeways. So it gets really into the crux of where people are working today to start connecting those vehicles together and actually deploying them on open roadways to try to make traffic a little bit smoother overall. With that, I think I'd like to wrap up and take whatever questions may remain. Thanks for your time and attention.